Welcome back, everyone. Today, we're diving straight into part 4 of our 6-part explainer series on the Merg-E language. If you've been following along, you know Merg-E is absolutely purpose-built for the Web 3.0 Innowinley stack. In the first 3 parts, we covered the surface-level syntax and data structures. But today, today we're opening up the engine room. We're getting into parts 12, 13, 14, and 15 of the language specs, breaking down the exact mechanics of how this language operates under the hood to guarantee security and determinism. To give you a sense of our scope today, we're transitioning away from just how the code looks. We're going to trace how code is defined, how it's owned, manipulated, and ultimately scheduled by the runtime itself. Merg-E operates on a very specific philosophy. It assumes absolutely nothing, it strictly controls data sharing, and it completely decouples your code from the underlying hardware's parallel execution capabilities. By the end of this explainer, you're going to see exactly how that philosophy comes to life. So, here's the bottom-up system design we're tackling today. First, robust integers. Second, ownership and capture. Third, iterators and actiquitos. And fourth, abstract schedulers. Okay, let's jump right into section 1, which covers part 12 of the specs, robust integers, specifically bit widths and type safety. Now, Merg-E makes a really vital distinction between runtime types and virtual line parse time types. It's kind of fascinating. Runtime representations, like whole4 or int2, actually exist at power of 2 bit width sizes in memory. But during compilation, the parser uses these virtual types, like v-whole5, which have a single expression resolve time. Basically, the compiler uses these virtual types to calculate the exact bit width expansion required for an operation before settling on the most efficient runtime type. It's a highly structured way to guarantee type safety without bloating your runtime memory. Let's look at a real-world application of that type math. Say you multiply a whole4 by a whole4. The result literally cannot safely fit into another 4-bit integer without risking a massive overflow. Multiplying 2 4-bit integers mechanically requires an 8-bit result to cover all the possible values safely. So by using integer bit width generics, the Merg-E parser just automatically promotes the result to a whole 8. This type math guarantees that your invariants are preserved. No underflows, no overflows, no reduced fidelity. It's prioritizing safety over the convenience of tiny numeric types every single time. Moving on to section 2, which brings us to part 13 of the specs, ownership and capture, the rules of possession. In Merg-E, every piece of data, even a simple scalar, has very strict operational properties. The language distinguishes between explicitly and implicitly shared data, sensitive versus non-sensitive, and mutable versus immutable. Take a constant for physical gravity, for instance. That's implicitly non-shareable, but explicitly mutable. So if Alice has a gravity variable and shares it with Bob, who, goes to space, him changing it shouldn't ruin Alice's local calculation. On the flip side, an API key is explicitly sensitive. It doesn't just float around the program, it has to be explicitly captured from a secure vault. Because Merg-E is designed to be safe by default, if you try to use operations that violate these capture rules, what it calls hazardous operations, the lexer is going to error out immediately. But, development requires some flexibility. You need to be able to test things. That's where the -- trust me bro compiler flag comes in. It's a pragmatic fallback. When you're testing code before you fully adhered to the rigorous ownership model, compiling with this flag lets you temporarily override the strict capture rules. But make no mistake, using this pervasively in a production environment is a terrible idea and highly non-idiomatic. All right, section 3. Let's get into part 14, iterators and actor-citos, or what we like to call the illusions of flow. Now, you might be wondering, why on earth doesn't Merg-E have for loops? It's a staple in literally almost every programming language out there. Well, the absence of a standard for loop is not an oversight. It's a deliberate design choice to keep the language implementation minimal. Merg-E wants to prevent deep, nested flow control inside functions because it considers that a bad practice. Instead, it leans entirely on structural iterators. Let's demystify how this control flow actually works. Step 1, as a developer, you might write an if or while statement because, yes, those do exist in Merg-E just to aid adoption. But in step 2, the compiler peels that syntactic sugar right back. It translates your while loop directly into a structural iterator. Then, step 3, that iterator maps the execution to small, ephemeral units called actor-citos. So basically, the control flow concepts you're used to are actually just macros built to prevent deep nested logic and force your code into bite-sized, schedulable tasks. So what exactly is an actor-cito? It's a strange little callable, an ephemeral, actor-like function with a lifetime that is strictly bound to the structural iterator that birthed it. Usually, if you're running an inline iterator, these run synchronously and just block their invoking parent. But when you start pushing Merg-E into parallel execution, these little callables require explicit handling. You have to manually juggle them, passing them through sorting functions to maintain the output order. It can definitely be a bit of a learning curve for newcomers. And finally, Section 4, Part 15, Abstract Schedulers. This is the real engine of the runtime. The crucial takeaway here revolves around the language's core mantra: no assumptions about parallelism. In Merg-E, you, the developer, do not control the threads, period. You can queue explicitly asynchronous actor CTOS, sure, but the runtime maintains ultimate control over parallel execution. A lightweight script testing runtime might execute everything sequentially, while a production Web 3.0 runtime might spread those exact same actor CTOS across massive thread pools. The language is completely decoupled from the parallel execution capabilities of the hardware. To visualize this abstract scheduler pipeline, at the base, in step 1, we have worker event loops. Now, these could be Python async tasks in the early testing runtime called Fafnir, or they could be actual OS threads in production. In step 2, these loops pull workloads from short queues. And dictating this entire process in step 3 is the overarching Nidahoger scheduler, which operates within the broader Yggdrasil architecture. At the end of the day, every workload is just a directed acyclic graph, a DAG, containing conditions, dependencies, and continuation points for the scheduler to manage. Which leaves us with a pretty provocative thought to wrap up today. How will these strict, low-level execution constraints, the mandated type safety, the rigorous ownership rules, and the decoupled parallel schedulers actually influence the broader Web 3.0 ecosystem? We've looked at the internal guts today, but what happens when this strict engine interacts with external data, asynchronous resources, and secure vault file systems? Well, we're going to explore that exact real-world utility in part 5 of our 6-part series. Thanks so much for tuning into this explainer, and we'll catch you in the next one.